Okay, can you hear me now? You should be able to hear me now. So how is everyone this afternoon, evening? All's well in America. Hope all is well wherever you are. We have a easy week coming up. Doesn't seem like it ever is, does it? But we somehow struggle through. Push on, one step in front of the other. So today, we're going to talk about, where the hell is my pen? Damn it. We're going to talk about angular momentum. Somewhat okay. Music is loud. Too loud. Ah, had it. Had it. I guess that's good enough. Okay, angular momentum. Remember what momentum is? Momentum is a property of anything that's moving. And when we talked about linear momentum, we said it was P, a vector, equals m times v. That was mass times velocity. So with angular momentum, we're going to call it L, capital L. And remember, when things are spinning, we cannot use m. We have to use the moment of inertia of an object, which is I. Remember, anytime something's spinning, mass turns into I, moment of inertia. Hey, Shocker Cat. And v, since it's rotational, we turn it into omega. So P equals mv for linear, for angular. L equals I omega. And both of these are conserved. Conserved. If no external force or torque So let's think about the conservation situation here. You've seen ice skaters, right? Ice skaters, they'll be spinning and they'll have their arms out. And when they bring their arms in closer to their body, you notice that their angular velocity speeds up. That's due to the angular momentum conservation. Nothing they're doing. It's just a property of the universe. So let's look at that scenario here. We'll draw a head, a body, there's their skates, and they're spinning. Oh, they're spinning like this. It's one thing I wish I had better handwriting and drawing. Guess I could work on it. So for this scenario here, we've got to figure out what I is. What is the moment of inertia of a human body that's spinning with its arms out like this, stretched out? What do we do? Spinning like this. Well, we can model it as a cylinder. All right, here's a cylinder with 2 point masses. So a cylinder with 2 point masses. This music is irritating me. I don't like it. It's better. Too much piano. Piano's too loud. Let's try this. Too busy. Okay. So, what is the point mass of a cylinder? Or sorry, what is the moment of inertia of a cylinder? Is 1/2 mr squared. So r is the distance from the center to the edge. And then I of the hands, point masses, is just mr squared. So let's just say that each hand is 1 kilogram and the body is, I don't know, what is in British, what's the average mass of a person? We'll say the radius is 1/2 meter. That's a pretty wide person, isn't it? Hey, Deborah. let's make it 0.25. So R is 0.25 meters. And let's say that their mass is, let's say, 60 kilograms. So we can figure out what their, or sorry, their angular, how much they're spinning at. Let's say it's 2 pi radians is one circle. So it's 6.24. So let's say they're spinning at 1 radian per second. So omega initial is 1 radian per second. We can figure out what their angular momentum is. So L is the I of the cylinder plus the I of the 2 point masses, which I should put a 2 in front, of the 2 hands. I'm going to put body here, B for body, H for hands, times the angular velocity. So it's going to be I of the body, which is the cylinder here. So 1/2 mr squared plus 2 times mr squared. And these masses are different. This is the body, this is the hands. So 1/2 the mass of the body. This is all times omega, by the way. So 1/2 of, oops, I don't need to do that. Yeah, I guess I do 60 times 0.25 squared plus 2 times 1 kilogram times how far are they out? Let's say 0.5. So R in this is 0.5 meters. Horrible. This freaking screen I have to write on is so damn small. I don't know what is going on with this. Okay, so let's see if I can get some room here. Delete. I want to erase all that. Okay, so let's do all this math. So 1/2 of 60 is 30 times 0.25 squared plus 2 times 0.5 squared. It's going to be 2.4. So their initial angular momentum is, momentum is L. L equals 2.4. Hey, Greg. Radians, kilogram radian per second. Oh my gosh, I don't like this brush. Everything's a problem, isn't it? So the I initial, or sorry, L initial, damn it. That's better. It's too thick. So L initial is, what did I say, 2.4. And that's going to be kilogram meter squared per second. So let's say then they bring their arms in. Okay, now they've got their arms out and they're spinning and they want to speed up. So they instead of having their arms out like this, they bring them in. When they bring them in, they're going to have to spin faster because this moment of inertia is going to decrease. So let's draw them when they have their arms in. So here's their head. Hey, Exploring Ginger. Their arms are here now, pretty much in line with their body. So we don't have this part anymore. This part's gone. So it's just L final is equal to I of the body times omega final. And I of the body is going to be 1/2 of the mass of the body times R squared times omega final. So the mass is not this mass anymore, it's the addition. So it's 60 plus 1 plus 1, it's 62. The radius is still 0.25 times omega final. We know momentum has to be conserved, so we have to equal it to 2.4. So now we can solve for omega f, and we'll compare it to this. So what we got here is 0.5 times 62 times 0.25 squared. We're going to 2.4 divided by that. That's 1.23. So omega f equals 1.23 radians per second. And you can see that it went up by about a quarter. Went up by 0.23. So that's why when ice skaters are doing their routines and they bring their arms in, they speed up in their rotation. And if you've been paying attention to the news the last, I don't know, 10 years or so, there's been some major earthquakes, like 9.0 and higher in South America and in Japan, etc. And actually, it redistributed mass on the Earth. So more mass of the Earth got pushed in closer to the center of the Earth. So based on that information, what do you think happened to the amount of our day? How did it affect our 24-hour day? Did it go up in time? Do we have more than 24 hours in a day now, or less? What do you think? So I'll rephrase this question. When you redistribute more mass towards the center of the Earth, what's going to happen to the length of our day? That's a question that you should be able to answer now. That's right, Deborah, it's less. Very good. Exactly. Because if you have more mass in the center, the moment of inertia has decreased, which means that our velocity has to increase, which means that our rotation time is not going to take as long. So we have a shorter day now. And that's actually been measured. But we won't notice it. It's microseconds. Microseconds shorter daylight, or daytime, 24 hours. No one's going to notice that. But it has real applications. And you've heard of stars that die, giant, massive stars. Well, you know the sun rotates. Sun is spinning. Spins on an imaginary axis. How do you spell imaginary? I-M-A-G-I-N-A-R-Y. Just like Earth does. This is an A. Damn, my handwriting is awful. Let's look up how fast the sun spins. How long does it take for sun to complete one revolution or one rotation? 27 days. So 27 Earth days for one rotation of the sun. So about once a month the sun does a complete rotation. It's pretty slow. We do one complete rotation in 24 hours. So some of our sun is pretty small, or pretty average, I'd say. Hey, Milan. It's a pretty average star. It's nothing fantastic compared to other stars in the universe. Some of them are much, much bigger, maybe hundreds of times bigger. So when they die and they collapse on themselves. The star goes from this big to this big. So what happens to that rotation speed? It speeds up. And stars, when they die, they emit all kinds of energy out into the universe. So when they start spinning faster, it sends a pulse out in a certain amount of time. That's what a pulsar is. So whenever that wave of energy hits Earth and is detected by telescopes, they can predict when the next pulse will be, because it's a pretty constant speed. trying to think of other examples of this. Angular momentum. That's about it, really. So if you ever find yourself spinning and you want to slow down, what do? You stretch your arms out. Get as much mass away from your center of axis of rotation, and you'll slow down your rotation. All right. Let's see here. Let's go on to something different. Let's talk now about, let's totally change gears here. Let's talk about buoyancy. So I'm going to ask you a question before we start. Let's say that I have a container, or not a container, a brick. A brick? Yes, Archimedes' law is similar, yes. Let's say I have two of these bricks. I'll try to draw them the same size. My art skills are horrible. That's not too bad. Do I agree with daylight saving time? I think it's kind of dumb. I think it's served its purpose in the past, but now it's not necessary anymore. But I don't know. I haven't really tried it. I've never not had it, so I don't know how I'd feel with it being different amount of daylight, like in the morning and at night. I don't know. I don't think it really matters. I do think it does cause health problems for people. The most heart attacks occur during these stupid time changes. All right, so let's say I have two of these bricks. One is a brick of lead, and one is a brick of wood, and they're the same volume, and they're put in water. Same volume. But you know the masses are going to be different, right? Different masses. And they're submerged underwater. Which one is going to have a stronger buoyant force on it? Let's say this is a pretty light wood, like a balsa wood or something. Actually, it's the same. It's a trick question. Because it doesn't matter what the mass is of the object, it only depends on the object. The buoyant force only depends on the volume of the object. Lead, metal, heavy metal. Heavy metal. Right. Led Zeppelin, exactly. So, that's a common, very common misconception people have about buoyancy. Like, you've ever been in a pool or the ocean, you know that you feel lighter, right? You can hold people up because they're lighter. Their mass doesn't change, but the water force pushes up on them, on the person, on the object. And it doesn't matter what the mass is, it's only the volume. So let's see how this works. Dropping a penny and a rock from a tall building. Hey, Duck College Debt. There is a buoyant force in air, but air is so has such a low density, it's negligible, it doesn't really matter. You're talking about air resistance. And yes, that would matter. Mass does matter with air resistance and the shape of the object. So a buoyant force, get my pen. Buoyant force depends on the weight of water the object displaces. This is a difficult concept. Students at school have a hell of a time understanding this concept. Buoyant force. Buoyant force is the force that the fluid, the water, pushes up on something with. So if you think about this, take an object and you put it in water. Right? Let's say you have a glass full of water and you put some ice in it. What's going to happen to the liquid water? It's going to overflow. Okay, so it's going to overflow and you're going to displace water. So if we could capture that water that was pushed out and weigh it, that's the actual force that the water is pushing on the ice with, the liquid water. So let's just take an example here. Here we have a container and water here, and I have a ball. Got a ball like this. It's three-dimensional. This radius r. Okay. So, and this is water. So what is the buoyant force? Well, the buoyant force is the weight of water. The weight of water would be the mass of water times g, right? So how do we figure out how much water is displaced? So we're going to need to use the density equation. So remember, rho is the Greek letter rho, is density. Okay? And then m is mass, and v is volume. So we need a mass of water displaced. Well, that's where we're going to get it. So density equals mass over volume. It's a ratio. So the density of water is 1,000 kilograms per cubic meter. Mass, we don't know. The volume we can get is R. Or sorry, that's an equation for the sphere. So the volume of a sphere is 4/3 pi r cubed. So let's say that our R here, let's say it's 0.5 meter ball. So we plug that in here, so 4/3 times pi times 0.5 cubed. Why did I put squared over here? So 4/3 times 3.14 times 0.5 cubed is 0.52. Multiply that by 1,000, and we get 523 kilograms. So that goes here. So 523 times 9.8. 3 divided by 9.8. It's 5,125 newtons. Now let's go back to this. We can say that rho is mv, so what we can do here is mass is really rho times v. So we can say the density of the fluid times the volume of the object times g. But another way to calculate is what we just did, really. So that's why you don't really need to know the mass of the object. You only need to know the density of the fluid and its volume. So the weight of the fluid the object displaces. So if you think about these giant ships, cruise ships, aircraft carriers, it's enormous stuff. How do they float? Well, let's do a problem. Say you have here like this. Here's an awful drawing of a ship. Horrible. Oh my gosh, it's so embarrassing. How is it possible that someone has zero art ability? I don't even know how to draw a ship. It looks like a ship. I guess that's okay. Let's say that this thing is... Oh geez, look at this jerk again. Remove. Hide user. Let's see what he wrote this time. Something really inappropriate. Why is that showing up still? Report. Hateful speech. I don't know, who cares? Okay, so we're going to go over here. Let's see what he wrote. In fact, let's not. Who cares? All right. So let's say the mass of this ship is 1,000,000 kilograms. Actually, no, Deborah. When you have something submerged, the fluid pressure is the same at all locations around it. They push equally in all directions. Like that. Okay, so we have weight acting down, and we have to have something acting up on it, which would be the buoyant force. If this was on a solid surface, it would be the normal force, but it's in liquid. So we need to figure out the volume this ship needs to be in order to float. So here we go. So sum of forces equals MA. So we have mg down minus the buoyant force up equals 0. So the buoyant force has to equal mg. So this is the mass of the ship. I'm going to say mass of ship. So remember, the buoyant force is rho. Is it rho Vg? Yes, rho of the fluid, V of the volume of the ship, times G equals mass of ship times G. So the G's cancel. So you get the volume of the ship has to equal the mass of the ship over the density of the fluid. Surface tension? No. The surface tension only exists at the surface, and that's due to the hydrogen bonding between the water molecules. So we have 1,000,000 kilograms, hey John Wright, over 1,000 kilograms per cubic meter. So this cancels with this, so it's 1,000,000 divided by 1,000. So these 3 zeros are gone. So it needs to be 1,000 cubic meters. So that's how much water this ship has to displace. So then the engineers then have to design a ship that will displace 1,000 cubic meters of water in order for it to stay afloat. So that's what engineers do. People that design ships, I forget what kind of engineering it is. That's that. Waiting for us. So now you know why things float. Because when they're submerged in liquid, the liquid pushes up on the object. Pushes in all directions actually, but it fights against gravity. Any questions about this? That's how they do it. They're displacing a lot of water. A lot of water is being displaced. They use a dinghy. All right, that might be a good place to stop for today. We've covered a lot of stuff in this class, so I don't know what else you would want to learn about. Anyone have any other topics they'd like to learn about? And maybe I'll know about some of it, maybe I won't. Hey, Boo Boo Bear. Well, it's both, Greg. You have to know their weight, so that you know how much volume they have to displace. Like a real small dinghy doesn't have to displace a lot of water, but a giant cruise ship, that's why they have that so much. They have that portion under the water that goes under like this, kind of triangular shape that goes down, so it displaces a lot of water. No problem, Ben. So can anyone think of any topics that they'd like to talk about next week? Are you stumping Dr. Fell today? What does that mean? Okay, air resistance. That's a good topic for next week. So next week we'll talk about air resistance. Any other requests? Yeah, Ben. Nothing else? Okay. I don't think Physikē has a premiere today. I think that he's taking a day off. Deo, I believe, is on at 3. Let me check. Hey, Dio. Greg will think of some. Okay, second, switch. Dale. Dale's on at 3:30 like usual. So you all have a break. You got about 50 minutes until Deo's premiere. He said it's a long one today. I gotta get my act together. I was so busy at the end of the year. So busy. That I couldn't get my act together to get a premiere up. That's all right though. Next time, maybe next week. All right, thank you all for coming in and hanging out. Shaka Cat, Milan, Katarina, Greg, Deborah, College Debt, Boo Boo Bear, Ben King. Thanks for coming, and we'll see you soon.
10.
Let's go for main engine start.
6, 5, 4, 3, 2, 1. And booster ignition liftoff of Space Shuttle Discovery, taking the space station to full power for full science.
This is Mission Control Houston.
Discovery roll program.
Roger roll, Discovery.
Discovery's roll maneuver is complete. It is now in a heads-down position on track for its flight to the International Space Station. Discovery flying 365 miles per hour, 1.5 miles in altitude, 7 miles downrange from the Kennedy Space Center. Discovery's engines are throttling down as the orbiter passes through the area of maximum pressure on the vehicle.